Let's continue our conversation, our discussion about rates of change, instantaneous rates of change. I mean, we use average rates of change to get to instantaneous rates of change, and slopes of tangent lines. So that's what we've been working with in this section. So we've been talking about rates of change and slopes of tangent lines, and we are going to take these and we're going to give them a name. We're going to give them a definition called the derivative of a function of a number at a number a. The derivative of a function f of x at a specific number a. So here's what we're going to do. We're going to say, basically, if you think about what we've been doing this computation at a specific value of a. And we've been saying, okay, so if we wanted the slope of the tangent line to a function at x equals 2, or at the point, say, 2, 8, well, then we've been able to compute that. And let me pull up an example, and we'll show that on the screen. So here we have a graph. We got a function and we want the slope of the tangent line, the red line on the graph, and we actually have two definitions that we've used to work with that. And we've plugged in specific numbers for a, right? In our definition, it's a generic a, but we've done all of our computations for both of these definitions using a specific value for a. So plugging in a numerical value for a, and then either letting x approach a or letting a distance away from a, we call it h, approach 0. So that's what we've been doing. But if we wanted to find the tangent line at more than just one point, if we wanted to find the slope of the tangent line or the equation of the tangent lines at more than one point on this curve, then we would want to probably do this computation generically for just any a in the domain of that function, and then be able to plug in the specific values when we needed an actual computation for the slope for whatever reason we want to know what the slope of the tangent line is. It would be nice if we could do this for a generic a, come up with a formula, and then plug it in, instead of having to every single time go through this limit computation and all the algebra that's involved. So that's what we're going to do with our new definition, and we're going to call it the derivative. Okay. So instead of going through a long limit computation and all the algebraic manipulation that's involved in that, we're going to do that every time we want a slope of a tangent line or an instantaneous rate of change. We're going to do this. We're going to say, let's define a new quantity called the derivative. And we are going to call it, this is actually in words, this says f prime of a. And what we say when we say that, f prime of a, that is the derivative. It's the derivative of f of x at a. Okay, at x equals a. Let's go ahead and write x equals a. At x equals a. So this is the shorthand that we use when we say it out loud. We say f prime of a. That little notch there with the f, that means f prime of a. So we say that f prime of a, and it is representing the derivative of f of x at a. Now, I want to be really clear that this is the exact same definition for the slope of a tangent line at a point a. So what we're doing is we're just giving that a new name. So instead of writing m sub tan anymore, I'm going to start using f prime of a, and we'll know that that means the slope of a tangent line. So we are talking about a slope of a tangent line. And by the way, the slope of a tangent line, a slope is always a rate of change, so that represents an instantaneous rate of change at a point. Okay, now this is, of course, we have the caveat, this is when this limit exists. So f prime of a is equal to the limit of the ratio f of a plus h minus f of a over h as h goes to 0 as long as that limit exists, if this limit exists. So this is our new definition. This is the first time we have had an official definition for what we call the derivative. So this is the derivative of a function at a point a. Now, by the way, all this, I just kind of talked this through, but this little note right here, the tangent line to a curve at a point is the line through the point whose slope is equal to f prime of a. Therefore, m sub tan is equal to f prime of a. So I just talked that through up above, but there it is in typed up form. Now, this is the form, the highlighted form is the form that we will use for the most part. It's the primary form that we're going to use for the derivative of a function at a. But our other definition gives us a second form as well. Remember, we had two definitions for the slope of a tangent line, or that instantaneous rate of change. And so we do actually have this second form down here, right here. And the prime looks really tiny on the type, so I'll put the prime in a little bit bigger. So we do have this second form that comes out of that first definition that we had. So by the way, this is, right, if you can think this was actually our second definition. This is from definition 2, and this guy was from definition 1. But we do actually use the first format that I have here that came out of our definition 2. But we have a second one as well. So we have a second form of the derivative. Okay? All right. So let's do this. Let's do it for a specific example. And I actually wrote up the example. This is the example we're going to do. Find the derivative of this function at a. So not at a specific point. We're going to actually find it generically at a. And then we'll use it to compute multiple slopes of tangent lines. So let me pull that up on the big screen. All right, so here we go. We've got this parabola, and we want to find the derivative. Now remember, when I hear that word derivative at a point A, so at a specific point A, here is the definition. And this is, again, right out of what we just defined, but I'm going to put it up here. This is going to be the limit of f of a plus h minus f of a over h as h goes to 0. And just as a reminder, this represents the slope of a tangent line. The derivative represents the slope of a tangent line to f of x at x equals a. Okay, that is how it is defined. So I'm just rewriting what we already had up on the screen in typed up form just a minute ago, but it's off the screen right now. So I want to have it here so we have it to work with, that formula to work with. So that's what we're going to do. So we're going to come in here, we're going to say, okay, let's figure this out. So let's find the derivative. Let's find at a, let's find f prime of a. So f prime of a, we got to take a limit. It will be as h goes to 0, and we're going to have f of a plus h minus f of a. And again, in the previous examples that we've worked with, we've plugged a number in. We've had an actual number because we've been looking for it at a specific value, like say x equals 2 or x equals -5, whatever it might be. But now we're doing it for this generic a. So remember, a is representing any point on this function. So we're going to get in here and look at how our function is defined. This is going to be a plus h squared plus 5 times a plus h plus 2 minus the function evaluated at a, f of a. So that's going to be a squared plus 5a plus 2 all over h. And now I just have to do some algebra. If I were to try to plug in h equals 0 right now, I'd get a 0 over 0. And so I want to get this expanded before I try to evaluate this limit. So get this guy expanded, we'll have a squared plus 2ah plus h squared, distribute the 5a plus 5h plus 2 minus a squared minus 5a minus 2. And we're going to have some canceling and simplification here. So the a squareds are gone, the 5a gone, the 2 cancels, and I notice that what's left behind has all the terms that are left behind actually have an h in them. So I'm going to go ahead on my next line. I'm going to do a lot of steps on one line, but I'm going to factor that h out. So I'll have 2a plus h plus 5 all over h. Kind of looking ahead, seeing I had that h in the bottom. Those will now cancel. And now I just have the limit as h goes to 0, the limit of 2a plus h plus 5 as h goes to 0. And of course, as h goes to 0, when this term goes to 0, I can do a direct substitution. Remember that a is a constant, so we're not taking the limit as a does anything. A is just a constant in terms of this limit. So we're letting h go to 0, so my result will be 2a plus 5. And it should be. My result should be a formula based on where we were looking for that slope of the tangent line at whatever value a might be. So this is what we say here is we say f prime of a is equal to 2a plus 5. Or we could say the derivative of the function at a is 2a plus 5. So we could actually write that out. We could say the derivative of the function f of x at a. Okay, that's what we're actually looking at right there. So we have calculated the derivative of the function at a. All right, well, how can I use that? Like, why would we want that formula? Well, it's as I was saying before, it would be because we might want to do something like this, right? If we only needed to find the slope of a tangent line at a single point, it's easy enough to plug in that value for a and compute that limit just one time. But what if we wanted the slope of the tangent lines to this curve at multiple places, right? We wanted to know what's the slope of the tangent line at -2? What's the slope of the tangent line at -1? What's it at 0? What's it at 5, right? I don't want to have to go through and do, before we had this formula, I don't want to go through and do that limit 4 different times or however many times. I want to have just a formula that I can plug into, because what I can do now is I can just say, oh, okay, well, I have it up here at the top of the screen. There it is. That tells me what the derivative is at every point. And again, remember that the derivative of a function at a is the slope of the tangent line at a, as long as that limit exists. So we can plug in to each one of these, just find f prime of -2. That's going to give me the slope. So if I plug in f prime of -2, 2 times -2 plus 5, that's going to be 1. I can plug in f prime of -1, and I'm going to get 2 times -1 plus 5, so that's going to be 3. I can plug in 0, and 0 is just going to be 5. I can plug in 5. F prime of 5 is going to be, 15. Okay? And each of those represents the slope of the tangent line. Each one of those represents the slope of the tangent line at those points. So these are slopes of tangent lines. And in the next section, we're going to come back and we're actually going to talk about, look at what's happening with these slopes. As we go from -2 up to 5 on this parabola, notice that the slopes are getting ever increasingly steeper and steeper and steeper. And that is interesting behavior, and that's what looking at these derivatives, these slopes of these tangent lines, can tell us about a curve. We can see that this curve is getting ever increasingly steeper as we go. All right. Okay, let's compute one more derivative. Let me get that up on the board here. You can see it all at once. Okay, and so there's the power of having a definition for what we call the derivative, which represents the slope of the tangent line at a specific point. We can calculate that derivative and then just utilize that formula. It's super convenient when you have to compute multiple slopes. All right. Let's do one more. This time, let's look at g of x equals the square root of 9 minus x. And let's do the same thing. I don't have the instructions up here, and rather than scrolling, I'll just state them out loud. We're going to find the derivative of this function at a, and then utilize that to answer part b. So we're going to find g prime of a, and then utilize that to find part b, where we want to actually know the slope of those tangent lines at more than one point. Okay? So we're going to come in here, we're going to say, okay, let's remember, so we're talking about g prime this time. So g prime of a is going to be equal to the limit of g of a plus h minus g of a all over h, as h, that distance between those two, goes to 0. So always remember, right? I mean, it's one thing just to memorize a formula, but you'll have a better time remembering it if you understand where it comes from. So remember that this is actually representing a slope between 2 points, a secant line, and then we're letting the 2 points get, the second point get as close, infinitely close, so that the distance between the two is 0, right? Approaches 0. So we're looking at a slope formula as we're letting those 2 points on the secant line get very, very close, so we can calculate the slope of a tangent line. All right, so let's do it. So let's find g prime of a. I'm going to zoom in just a little bit here. So let's find g prime of a. That's going to be the limit of the square root of 9 minus a plus h minus the square root of 9 minus a. all over h as h approaches 0. Oh, my 9's and my a's look awfully similar. There we go. Okay, so let's keep this going. I notice in the top, not a whole lot's going to simplify, but I notice that if I were to try to plug in h, and again, I won't write up this thought bubble, but it's going on in my head. If I try to plug in h directly, the two roots would be exactly the same. So they would cancel and become 0, and the bottom would be 0, and I'd have that 0 over 0, which always means, do more work. So I'm looking at this and I'm thinking, I've got roots, and so the best way to handle these roots would be to use the conjugate. So we've got 9 minus a minus h minus 9 minus a under a root all over h, and we're going to multiply top and bottom by the conjugate. 9 minus a, I'll try to make my a's and my 9's look different, plus the square root of 9 minus a. And of course, whatever we do in the top, we have to balance by doing the same product of the h in the bottom. So we'll multiply top and bottom of this expression by that conjugate, and then we distribute. And very nicely in the top, when you do multiply a root expression by its conjugate, we end up with 9 minus a minus h and minus 9 minus a. The roots cancel. We get a square root of a perfect square, and in the bottom, 9 minus a minus h plus the square root of 9 minus a. All right, so let's see what happens. Now in the top, notice that when we expand and distribute that negative sign, we will get lots of canceling. So the numerator is going to simplify down to simply negative h. Now the denominator, we still have this h times 9 minus a minus h plus the square root of 9 minus a. And I think I went off the screen, so let's bring that over. Okay, and that's what we end up with there. And then to finish this out, we've got the limit of simply, oh, notice now also, well, let's write it out. So all those canceled, and then we had minus h over h times the square root of 9 minus a minus h plus the square root of 9 minus a as h goes to 0. Now notice that the h's now cancel from the top and the bottom, so I have just 1 in the top. And so now what we're looking at is just the limit of negative 1 over those two roots, 9 minus a minus h plus the square root of 9 minus a as h approaches 0. All right, and now I can actually let h go to 0, and so as this goes to 0, as h goes to 0, approaches 0, what we can do is we can say that g prime of a, our function was g, so g prime, the derivative of g at a, is actually equal to negative 1 over, well, notice what happens. When that goes to 0, we end up with 2 of those square roots. They're exactly the same. So 2 times the square root of 9 minus a. And that is my derivative, which remember that the derivative represents the slope of a tangent line at the point A. So this represents the slope of the tangent line, and I'll keep saying this over and over again like a broken record because I want us to always remember, right, we do this computation and there's lots of mathematical calculations done here, but I want to remind you, and I want you to remember what it is you're doing. You're calculating an instantaneous rate of change at a point, or a slope of a tangent line at x equals a to the function g of x. Okay? So that's what we're actually computing. All right, so we used our conjugate, used some limit tools here, got our derivative, and now we could actually use it to find those slopes, right? Bringing us back around to what does it mean? So now we can actually find the slopes of the tangent lines to this curve at specific points. So if a equals 1 or if a equals 8. So what would we do? Well, rather than having to go through this whole process and actually plugging in, wherever there's an a, having to plug in a 1 or an 8 and doing this limit 2 different times, if we do it once with this generic formula, now all I have to do is plug it in. So to find g prime, to find the slope of the tangent line at a equals 1, I just find g prime of 1. And I have a formula for g prime of 1. So a formula for g prime of a. So I plug in 1. So -1, I'm going to keep it up there at the top. -1 over 2 times the square root of 9 minus 1. And of course, that's just -1 over 2 times the square root of 8. And that's a little bit unsimplified. So we could keep going and say, okay, well, that would be -1 over 2 times, square root of 8 becomes 2 root 2. So that would actually be 4 root 2. Still don't really love that because of the root in the denominator. So we'll just continue to simplify that down a little bit. So we've got minus root 2 over 8. And we can leave it like that. Okay? And that is a much nicer form. That was all just some algebraic simplification. Let's do it for 8. So g prime of 8, -1 over, there's my formula right there, 2 times the square root of 9 minus 8. Well, 9 minus 8, of course, is just going to be 1. So this is -1 over 2 times the square root of 1, or -1/2. And there we go. So there's a nice computation of the derivative at a point for a root function, and then utilizing that actual derivative at a point to find those slopes too. So always reminding ourselves, what is it that I'm doing when I'm calculating a derivative at a point? I'm calculating a formula for the slopes of the tangent lines, and then I can use it to find those slopes of the tangent lines. Or an instantaneous, also you can think instantaneous rate of change.